Hello again. This is Math 2232 coming to you from the College page. And the title of this lecture is Arc Length and Surface Area in Polar Coordinates. As always, be attentive while watching this video. So we're going to be talking about some more applications of calculus and integral calculus and how we do them in terms of polar coordinates. And we're going to start out just like we did last time. We're going to assume, as we're looking at arc length, that r is equal to f of theta, and theta runs from alpha to beta. Now, we already said that this happens sometimes, not always, but that's our assumption here. And we also are going to assume, as we did in the arc length section, the curve is traced out exactly once, just as we did in previous sections. But now we go back to the polar coordinates. So we have x is equal to r cosine theta, y is equal to r sine theta, but r is f of theta. So x becomes f of theta cosine theta, and y becomes f of theta sine theta. So now we have x and y parameterized with a common parameter of theta. So now we can use our theory from parametric equations. So we'll compute dx d theta here using the product rule, and dy d theta here using the product rule as before. And as before, these simplify thus and thus. So we have this expression for dx d theta, this expression for dy d theta. And what we're going to put under the square root is dx d theta whole squared plus dy d theta whole squared. So I'm going to be squaring this plus squaring this. And when I expand it, some nice things happen. So I expand it, and what you see is here is dr d theta whole squared times cosine squared. And over here I will have dr d theta whole squared times sine squared. So cosine squared plus sine squared is 1, so that ends up being dr d theta whole squared. Similarly, here I have r squared sine squared theta and r squared cosine squared theta. Again, sine squared theta and cosine squared theta equal 1, so I get r squared. And here, this term is exactly the negative of this term, so they cancel out. So you see, this is the expression I get in polar coordinates. And that's what I'm going to put under the square root. So the arc length formula for polar coordinates is then L is equal to the integral of ds. But in this case, in polar coordinates, ds is equal to the square root of r squared plus dr d theta whole squared d theta. Let's use this to solve a problem. Here, I'm asking you to determine the length of the curve given by r equal theta for theta between 0 and 1. You know what to do. Let's see how you did. Now, this curve actually starts here and starts growing and growing and getting bigger and bigger and bigger. And this is called the spiral of Archimedes. And this type figure is actually often found in nature. And here it is graphed between theta going between 0 and 4 pi. We're not going nearly that far here. But what you're going to do is we're going to use our formula. So this is going to be r squared, which is theta squared, plus dr d theta is 1 squared. We have that, and this is d theta. So L is the integral from 0 to 1 of the square root of theta squared plus 1 squared. And this is nice because it allows us to review trig substitutions, because that's how you would compute this, and I would expect you to compute it. So we're going to let theta in this case equal the tangent of theta. D theta then is going to be secant squared x d theta. This is theta is equal to tangent of x. I think I misspoke. And d theta is secant squared of x dx. And what happens is that as when theta is 0, x is 0, and when theta is 1, x is pi over 4. And this square root is going to be tan squared plus 1, which we know is the square root of secant squared x, which is the absolute value of secant, but between 0 and pi over 4, that is positive, so that is just secant. So then this is going to be the integral from and again, I'm integrating dx here, so the limits had better be x's. This is 0, pi over 4. And again, for probably the dozenth time in this course, we get secant cubed of x dx. We integrated that by parts the first time we saw it, and now we probably just know immediately to put this in, and we substitute the values of 0 and pi over 4. These are special triangle values, so you should be able to get that and simplify it. And so the exact answer is 1/2 times the whole of the square root of 2 plus the natural logarithm of 1 plus the square root of 2. That is the exact answer. Let's do another problem. Find the arc length of the cardioid, r equal to plus 2 cosine theta, and we're going around the curve once. You know what to do. Let's see how you did. All right, so what we're doing is this is going to be, and here we're writing this as r equal f of theta, so we're taking 2 plus 2 cosine theta whole squared, and f prime, the derivative of r with respect to theta, is going to be minus 2 sine theta, but we square that as well, and we integrate this 2 theta, and we're going all around the cardioid, and this is theta, so it's period 2 pi, so we go from 0 to 2 pi doing it once. Now we expand each of these, and we take note of the fact that cosine squared theta plus sine squared theta again is 1. So we simplify that, and we get that this is the square root of 8 plus 8 cosine theta d theta. Now we can get a 4 out of there, and the square root of 4 is 2. Pull that all the way through. We have 2 plus cosine theta d theta. And now we're going to use the identity that the cosine of 2 theta is 2. Or actually, this is alpha. The cosine of 2 alpha is equal to 2 cosine squared alpha minus 1. Now this is really just a recalibration of what we've done before, and it's either called the half angle formula or so on. And so what happens is I make this substitution here, and I substitute in, and 2 plus 2 cosine theta becomes the square root of 4 cosine squared theta over 2, and the square root of theta squared over 2 is cosine, absolute value of cosine of theta over 2, and that's and the absolute value is positive, and in fact the when we take into account the signs and we do the calculation, this is a pretty easy integral. You should get 16. You should check these details for yourself. Now you might say, well, what about surface areas of revolution in polar coordinates? Well, I got to tell you, it's going to work pretty much the same way. So we're going to start out again, r equal f of theta. And x is r cosine theta, y is r sine theta. You see this looks really familiar. And so what we get is that the surface area of revolution is either going to be, if I'm going about the x-axis, I get 2 pi y ds, or 2 pi x ds about the y-axis, but ds, in this case, we have another representation for it. This is the square root of r squared plus dr d theta whole squared d theta, where r is f of theta. So you see we have a different way to do this if this is polar coordinates. Let's look at a problem. Find the area of the surface formed by revolving this curve, r equal to cosine theta from theta equals 0 to theta pi about the polar axis. You know what to do. Let's see how you did. Okay, so here what we're doing is this was r is equal to 2 cosine theta. So that is the curve, and we know that y is equal to r sine theta. So that's what we're doing from 0 to pi over 2. We substitute that in. This is going to be r squared plus this is going to be dr d theta whole squared. So we square all that, and we get this, And we note that the definite integral from 0 to pi over 2 of sine x cosine x dx, or that could be thetas if I wanted to, from 0 to pi over 2 is going to be a half. And so I have 4 pi at the end of my answer. Now, we've really talked a lot, and this is kind of a summary slide, but you see the arc length is an important thing in Calculus 2. It's even more important in Calculus 3. And so we have this expression for arc length. We have this expression for the surface areas, and ds appears in all three of those, but we have 4 different ways to talk about ds. ds can be this if I'm integrating dx. ds can be this if I'm integrating dy. ds can be this if I'm integrating dt, and ds can be this if I'm integrating d theta. Wow, quite a bit here. Much, much more about this in Calculus 3. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.